Right. Okay. Good afternoon, ladies and gentlemen. How are you today? Good. So, again, let's recall what we have learned previously, and then we move forward to the new materials. So, last week we learned scientific notation and significant. This is called scientific notation, right? And we learned significant figures. So, please tell me how many significant figures here. Somebody say four, please kill yourself first. Okay, just kidding. Okay, three, right? Okay, and precision is that what's how good is the data, right? So and then after that you need to know how to do the addition, subtraction, multiplication, and division of the significant figures. That's what we had uh, on Monday, right? In your Kahoot. Okay, and then after that you have scatter data. I again scatter data means that I ask one student to do 10 same experiments, or 10 students do one experiment, right? So we have xi, we have range from large to small, and then we have mean, that means the average. So in order to understand the precision or how to evaluate scatter data, we have sample variance, or we call it standard deviation, right? Okay, so as a result, you can represent a data like this: x equal to x sub mean minus plus error limits. So error limits can be one standard deviation or two standard deviation, for example. It all depends on your definition. Okay, right. And after that, we talk about dimensional homogeneity. That means the dimension on the right will be equal to dimension on the left. So as you can see here, the dimension on the right need to be equal to the dimension on the left. And as you know, this is called Reynolds number. Reynolds number, this is called dimensionless quantity. So this is dimensionless. So if you have dimensionless value on the right, on the left, you need to have a dimensionless quantity on the left. Okay? So here we give you some examples of the dimensional quantities. I hope you all know this, and I want you to remember this well. Okay? So this is what we learned last week, and what we learned on Friday, on Monday. And then after that, we move to the another way of the another materials, which is the process data and how to represent the process data and how to do the analysis of the data. Okay, so as you know, if we have a scatter data, something like this, you need to plot a straight line. So this is one of the examples tell you that you need to have a straight line, and you need to find out how to do this job. I hope you learn something from. I hope you learn something. So, and after that, on Monday, if we have data like this, you can plot a straight line, right? And what happens if you have a data like this? You don't know how, you cannot draw a straight line. So what happens? You need to make it as a straight line, right? So I make an example for you. The result, the score of this course against the time you play games a day. Right? So this is one of example from this curve, and you make it become this curve. So you can do you can find the A and B, and so you can predict the data as you like. So the important concept for this idea is that from any non-linear equation, you make it become linear equation. So from x and y, you change to quantity 1 and quantity 2. This is what we learned. And here I give you the second example, which is the mass flow rate related to the temperature. So we understand there's a reason to believe that the mass flow rate varies linearly with the square root of the temperature. So as you know, if this is a linear relationship between the mass flow rate and the square root of the temperature, you can write equation like this. So this is the meaning of this sentence. Tell you that you can have a mathematical equation like this, and you started to find out A and B, and then after that you can predict. So when you do a raw data like this, you understand this is not a straight line. This is not a linear equation. So how to make it linear? You make square root of temperature, right? Square root of temperature. So this one will become square root of temperature. So you become like this. So from this curve to become this straight line, and you got A and B, you find the answer. So by the end of the lecture on Monday, we talk about this. So normally this is a common nonlinear function and make it become linear function equation. Okay, so like this, reciprocal of x or square root of x, right? And this is exponential function, and this is power law. So exponential function, I'm sure that, let me show you here again. I want you to remember this 4, which is important because the number 3 here, y equal to a times exponential b times x. So this is what we call exponential function. As you know, e is a 2.71a blah blah blah. Okay. However, and when you have a data like this, and you want to make it become linear, so you do the natural log to the both sides. Okay, natural log to the both sides, that will be natural log y equal to natural log a plus b, because natural log e will become 1, right? So you will become you will become b times x. So as a result, you understand here is that ln natural log y will be here, will be in y-x XL, and then x will be in the x-XL. So you can plug a straight line using this equation. Okay, and then next one is power law. Power law, again, you put this is y equal to a times x power b. So power law means that if you put the natural log in the both side to the equal this symbol, so you can have natural log y equal to natural log a plus b times natural log x. So as you know that if you have this equation and you understand this one in y-axis, this one will be a natural log y, and in the x-axis that will be natural log x. Okay. So have we talked about this on Monday? Have we? We haven't, or we did? Okay, don't worry. Let's do it again. Right. So first of all, when you have this set of data, y, you have y, you have x, you have y, you have x, y from 1 to 7. Sorry, x from 1 to 7, y from 1 to 49. And you start to plug a data. You start to plug it. So you have 1, 2, 3, 4, 5, 6, 7, and you have 1, 4, 9, 16, 25, 36, 49, something like this. And obviously, you understand this is not a straight line. So what happened? So this is one of the examples we call it power law. This is y equal to a times x power b. So that means what? If you do the natural log of x and y, if you do the natural log of x, if you do a natural log of y, you can get another set of the data. You understand, right? No problem. You do another set of data, ln x, so you got ln1 will be 0, right? ln2 will be 0.69, blah, 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 blah. You can do you can use your calculator to get this answer easily. lny will be what? From 0 to here. So now the question is, not the question is, you can plot ln x and ln y instead of x and y, because you know ln x and ln y can be a linear. Bingo, is a linear. Linear is linear. So if a 0, 0, that will be here, right? And this point will be 0.69 and this and 1.386. This point will be 1.099 and 2.197. Blah blah blah. So you got 7 points here, and you realize, wow, this is a straight line. So when you have a straight line, you can make an equation, right? Is y equal to ax plus b. So you can write down that natural log y equal to natural log a plus b times natural log x, because this is one. This is linear. And now the problem is how to find a and b. If you find a and b, you got this equation, and you can write a and b here, and you know how to predict when a is, for example, when x is 8, what's the y? Or when x is 3.5, 3.3, what's y? So the important thing for the mathematics is that how do you model the physical meaning, and then you realize that, and you can predict using a mathematical model. So this is a mathematical model, right? Okay, so find A and B. I don't want to waste your time, so it's easy for you to find out as long as you pick up 2 points and you get the answer. You get A and B, right? Okay, so here I want to tell you, is any important method, any other method to find out this A and B, or this is the only way to find out? So be honest, if I give you the data like this, and I didn't tell you this x, y follow power law, can you intuitionally, or can you guess this is power law? Can you? Maybe not, right? As long as I tell you this is power law, so you can plot x, y, and x, ln x and ln y. Otherwise, it's not easy for you to plot, to realize this is x and y follow the power law, right? Okay, so that's why that's why an important topic we are going to introduce you. Okay, so this is the conclusion of the 2.7c, fitting nonlinear data. So how do you fitting the nonlinear data, make it become linear? Okay, so there are 4 examples. Hope you remember there are 4 examples. Okay. These are the 4 examples, right? Reciprocal of x, square root of x, exponential function, and the power law. Okay. Right. So next topic we are going to talk is called logarithmic coordinates. Logarithmic coordinates, or you can call log coordinate. Log coordinates is what? This is what we normally understand. This is called rectangular scale. So this, you know, this is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And 11, 12, 13, 14, 15, 16, to 20, to 30. And this is x-axis. Y-axis is 0, from 0, 1, 2, 3, 4. So it's 10, 20, 30, 40. This is what we call rectangular scale. Rectangular scale. And how about log scale? Logarithmic scale. This is 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So as you can see that this is not in the same length. Okay, this is different type of scale. And this is what we call log scale or logarithmic scale. Have you seen this before? Log paper. Have you seen this before in your college, in your high school? No? Have you learned this before? No, you don't know. Right. Okay. So why we need this? Why we need this kind of paper instead of this paper? For example, this is what the data we just have, just in the previous example, x and y, right? X and y. So x and y 1, 2, 1, 2, 3, 4, 5, 6, 7, and 1 y is 1, 2, 1, 4, 9. So you plug something like this. So it's very difficult for you to understand, or very difficult for you to find the model, the mathematical equation to represent this line, unless I tell you this follow the power law. So if you know this follow the power law, you can plug something like this, right? That's what we learned in the previous example. So you use natural log x and natural log y to plug something like this. But this is rectangular scale. This is rectangular scale. Okay, so the important thing is when you sense this, is this an exponential function or not? If this is yes, of course you do something like this. You start to do the calculation and you start to find A and B. Is there any quicker way to find this? Yes, there's a way. If you have log paper, and you don't need to worry about this, natural log x or natural log y. You just put this number here. Put x and y in this place, and you can get a straight line. You say, yes, Professor, I know. This is a power law. Okay, so it saves your time, and you can directly tell me that, well, if these numbers fit put into the log paper, then you understand this is a power law. And you can use mathematical model to represent this data. Okay? So this kind of coordinates, we call it logarithmic coordinates. So as you can see that this one is log plot. This is log plot. This is rectangular plot. So important thing is that if you change from rectangular plot to become log plot, it tell you the same thing. You know, it's just a different type of scale. That's it. And you use natural log x to become x. Natural log y become y. Okay. So you put y become natural log y. You put x become natural log x, or you put natural log x become x. You put natural log y become y. Okay, so this is what we call log plot, or we call log plot. So this is log plot. So next Monday, if I show you a plot and I ask you, is this rectangular plot or log plot or semi-log plot or none of them, and you need to find out. You need to tell me the answer. Okay, if this show up in a Kahoot on Monday, coming Monday. So you might think that, well, Professor, is it possible to have a rectangular scale here and a log scale here? Yes, it is possible. And this is what we call semi-log plot. So again, let's go back to the power law. Power law is this. One, this is log plot, this is log plot, and this is followed by the power law. You have natural log in the both sides, and you got the answer. Okay, so this is power law. How about exponential function? Exponential function is natural log y equal to natural log a plus this is b times x. So once you want to show up this data in the paper in a scale, then this is what we call semi-log plot. What is semi-log plot? Semi-log plot is this is rectangular scale. This is log scale, right? From 0.1, 0.2, 0.3, 0.5, 0.6, 0.7, 0.8, 0.9, 1. 1 is 2, 3, 4, 5, 10, 20, 30, 40, 50. Okay, this is log scale, and this is rectangular scale. Okay, so this is called semi-log plot. You might want to say, well, Professor, why we need this kind of plot? So the reason we want to have this plot is, this scale is very long. From 0.1 to 100 is about 1,000 times. And from 0 to here is about 100 times only. So once you want to plot a data which is very far away to each other, I mean the data is very far away. So it's easier for you to use log plot to represent your data. And also it's easier for you to find out the mathematical equation if you use log plot and it becomes a straight line. Okay? Okay, so if the plot appear linear in semi-log plot or log plot, how to find A and B? So in your midterm exam, if I give you this data, I say please find this mathematical equation. Can you find out for me in your midterm exam? Okay, if I show you these 7 data and you realize this is a straight line and this is log plot, so you realize, wow, Professor, this equation follows power law. So you need to write down the power law. But there are 2 parameters in the power law. One is A, another one is B. So according to this data, can you find out A and B for me? And tell me the correct answer of this equation. Can you do that for me? Yes, you can, right? Okay. How about a semi-plot? That will be the same, right? So you just pick up 2 points. Assume these 2 points can fit this line, can represent this line very well. So you just pick up 2 points and write down. Give me the answer. Okay? Are you with me so far? No? Yes? Okay. My suggestion is you read my lecture note first before you come to this lecture. And it will be easier for you to digest what I'm trying to tell you. Otherwise, you might spend more time when you go home. I don't want this to happen to you. I want you to have a happy college life, right? Happy college life. Right. So this page show you, just give you an example. So please work. I don't want to waste your time. Just do this by yourself. I'm sure you can get the right answer. Right. So this is the conclusion. Conclusion is that power law, we follow log plot. Exponential function, this is what we call exponential function. We follow semi-log plot. Okay? Right. Here I want to give you some important examples. You might say, well, Professor, why we need to learn this? This is a semi-log plot. You know the fuel cell? Do you know fuel cell? No, it's very important for the car, right? You use lithium-ion battery for the vehicle, and now another technology called fuel cell. One of the important key component in the fuel cell is what we call catalyst. Catalyst is important for the fuel cell, and in order to find a good catalyst, that catalyst needs to be located in this point, which is very good. and very efficient. That's what we call this volcano plot. Volcano plot. It looks like a volcano. And x-axis is rectangular scale, right? From 0 minus 0 0.2, 0, 0 0.0, 0 0.2, and y-axis is log scale, log scale. And this is the volcano plot. This is another semi-log plot. This is the atomic number from 1, which is hydrogen, 2, helium, right? 3 is lithium, 4 is barium, boron, carbon, nitrogen, oxygen, fluorine. So from 1 to 90. And how about this one? This is log scale. This is the abundance of the atoms of, we use silicon as 1, as a 10 to 6 here as a standard. So as you can see, the element here is abundant, and you have very less you have very less you have very amount of the materials like rarest metals, or what we call the rare earth elements or precious metals in this area. So you have plenty of the material of the you have plenty of the element you have plenty of the materials in the crust. For example, like magnesium, aluminum, iron, or titanium. But you don't have enough elements like gold, right? Silver, gold, right? Uranium, something like this. So this is another semi-log plot. Right, does anybody tell me what's wrong with this? What's wrong with this plot? Does anybody want to tell me? 0.1 point, 0.5. Does anybody want to tell me what's wrong with this plot? Anything wrong? Anybody want to tell me? 0.5 points. No, you cannot find any problem. No. Listen, in the future, if you want to connect two dots together to become a one line, this need to be continuous. Okay, from one dot to another dot. If you want to make this dot to become one line, and that means these two between the dot between these two dots need to be continuous. Can you find something between boron and carbon? Can you find that? No, you cannot, right? So can you make boron and carbon together become a line? No, you cannot. You cannot. Okay, so remember this. So this part has a little bit problem. Okay, but anyway, this is out of the scope in our lesson. I just want to tell you this is a common sense. Okay, so I just introduced you the semi-log plot. How about log-log plot? This is log-log plot, what we call Rankin plot. Anyway, it's too far for you to understand. But what I want to tell you is that this is the plot you will see commonly when you go to the graduate school. Right. Okay. So the section 2.7e is fitting a line to scatter data. Apart from find out two dots, 2 points to become one straight line, you can use some of the mathematical models like linear regression or math of least square. You can find this easily in the book or in Excel. So we don't want to introduce this to you. Right. So this is what we learned in the chapter 2. Okay, do you have any questions for me? No? If you have and you hesitate to ask me, you are very welcome to come to approach me after the class, okay? Right, so let's go to the chapter 3. Let's move to the chapter 3. Again, we start from a very, very easy part. Chapter 3 is related to the processes and the process variables. Process variables like how to measure the concentration, how to measure the temperature, how to measure the pressure. Okay. So again, let's think of what is process. What is process? So once you have a process unit, you have input and you have output. Of course, before output, there are some you will go through physical change or chemical changes. And this change can be a reaction, can be filtration, which is physical, right? Reaction is chemical, filtration is physical, evaporation physical, heat change, energy change, right? And then you have output. Okay, you got product. This is process. So when we think of this, if we put the process and process together, become processes. So you have process A, you have process B, you have process C. Then you have a lot of streams. Not only one input, one output, but you have many input, many output, or many streams. And this is what we call process streams. Process streams. So for example, the process streams in the process unit B here are what? So if you think of this process B, then you will have one input, two output, right? So you have one input, which is input B, and you have two output, which are output B1 and output B2. So once you want to think of this process B, all you need is this to think of these three streams, not this one or not this one. Okay. So the rules of the chemical engineering in the process is that once you have process, you need to design the process, or you need to design the processes, and use the stream to make it together, to make it works. And then after that, you operate to make it works. Okay, so design is that you need to draw the flow sheet. I hope you remember this. Oh, you don't need to draw these pretty pictures like this. You can just draw a box and tell this is reactor, this is filtrator, or this is evaporator, something like this. Okay, so this is important to draw a flow sheet, process flow sheet. And then you need to make sure the specification of each process unit. So each process unit, you need to think of what is this? What's the size of this? Right? What's the specification? For example, this is a reactor, or this is a separation equipment, chemical, physical, or this is a heat changer. It's in terms of energy, not related to the mass. And you also think each unit, you also need to think of the variables, right? So you need to think of what's the pressure, what is the temperature, what is the flow rate, what is the fit, what's the component, or what's the composition of the fit. Okay, so after design, after you finish all the designs, you do the operation. So, and you make it works, right? So, and then after that, if this process run for a period of time, and you need to maintain the machine or maintain the process, and you need to have a troubleshooting once you have problem. Okay, so once you get product, you want to get more products, or you want to reduce the products. Well, that's what we call the bottlenecking or turn down. Okay, this is what we know. I hope you remember we have example like this in chapter 2. If the the yield is not good. Okay, if the bad Y batch per week, and you need to return. You need to stop the factory. You need to do the maintenance, or you need to make it better. Right. So this chapter is that the definition of the variables. So I want you to know how to measure the temperature, how to measure the pressure, how to calculate the concentration, and how are you going? What do you use? What's the tool you want to use to measure the temperature? What's the tool you want to use to measure the flow rate? What's the tool you want to use to measure the concentration? And then you need to know that we want to do the calculation of the variables. Okay. Right. So this is the section 3.1. So this chapter, the chapter 3, mainly want to tell you very basic knowledge. Even you learn this from your junior high school or high school. Of course, like section 3.1, mass and volume. I'm sure you know this already. Right? So if you put the mass and volume together, and you immediately realize we are going to talk about the density. Right? Because mass divided by volume will become the density. So, and you know that the unit of the density, you can have SI system, CGS system, or American engineering system. And if you reciprocal of the density, and what does this tell you? I'm so not. So this is volume and the unit of mass. That's what we call specific volume. So if you put how many grams, what's the volume per gram? That means it doesn't mean density. It means the specific volume. Okay, that's easy. So it's a reciprocal of density. Right. So this is a very easy example. Tetrachloride. Tetrachloride is a kind of solvent and greenhouse gas, and chemical. This is a very common chemical we use. Okay. So if you have a volume tetrachloride, if I give you the value of tetrachloride, I give you the density, and I want to ask you what's the weight of this tetrachloride. I'm sorry, this is insulting, right? Insulting you. But you don't want this, Okay. However, if I tell you this is a pound mass, 6.2 pound of the tetrachloride, and then I want to ask you what's the volume of in American CGS system, then you need to know that how many pound mass become how many grams, and you know the density, and you convert this to the volume. Okay. So I don't want to waste your time. So please do this calculation by yourself. Okay, so next term is called specific gravity. What is, we just learned specific volume. So what's the specific gravity? Specific gravity means this is also, again, this is a dimensionless quantities, because you have to, this density has to related to this density, or this specific gravity has to related to another density, like density divided by reference density. So in this case, in a common case, the reference will be the water. Water normally is 1, right? And so this is reference density. This is the density you are measuring or you want. So this is what we call specific gravity. And of course, density divided by density, this will become dimensionless quantity. Okay? And water will be the one normally we use as a references, especially at 4 Celsius. 4 Celsius. So in 4 Celsius, the density will be 1, right? 1 gram per cubic meter. Okay? So I'm sure this doesn't bother you at all. Right, so when you see something like this, specific gravity equal to 0.6 and 20 degree divided by 4 degree. What's this? So this tells you that this is 4 degrees, the water at 4 Celsius, the density of the water at 4 Celsius. And this is the reference, this is the measurement. Some substrates, you measure the densities at 20 Celsius. And the density specific density will be 0.6. Okay, so this expression tells you 2 information. The first information is 4 Celsius water. Okay, density at 4 Celsius. This is the density, the specific gravities of some substance at 20 Celsius. Okay. Right. These are some examples. I think it's easy, so I don't want to waste your time. Skip. So, example 3.1-1, mass, volume, and density. You want to measure the density of the mercury, and you want to measure you want to measure the value of the mercury using this weight amount of the mercury. Please work through this study by yourself, and I just skip this. Right. So now we want to discuss the density will be changed because the temperature change. That's what we call thermal expansion. So the value change, because thermal expansion means what? Value change. The value change will related to density. So once you have because the mass doesn't change, but value change, right? So this is one of example to let you know. You don't need to remember this. This is cubical thermal expansion of liquids. For some of the liquids, the value related to the temperature, and followed by this equation: Vt equal to V0 bracket 1 plus alpha T times beta T power 2 times gamma T power 3. You can get this equation in the chemical engineering handbook. Anyway, alpha, beta, gamma is a kind of parameter. It depends on different materials you use. Okay? So this is what we call parameter or coefficient. It depends on what is this. For example, this is water, or this is mercury, or this is methanol, for example. So here is one of example. Is that example mercury is that alpha will be 0.118, and beta will be 0.0078. And you know the gamma, because this is too small. So in the case of mercury, we just remove this term here. So you got equation like this. So if I ask you, wow, what's the temperature and what's the value of mercury at a certain temperature, and you can use this equation to find out the answer. Okay. So for the liquid has some equation. For the solid also we can have some equations. This is one of the equations to represent some certain solids, which is V2 equal to V1 bracket 1 plus C delta T. So the definition of delta T will be the differences between temperature 1 and temperature 2. Okay, and C again is coefficient. Depends on the different substance. Right, so this is the example. Again, let's skip this example and please read this by yourself. For this, the first section is there's three points. Like first one is mass, volume, density. You need to know the relationship. And the second point is that specific value and specific gravity, and the value related to the temperature. So temperature change, value change, density change. Right. So let's go to the section 3.2, flow rate. Okay, so the 3.2a is mass and the volumetric flow rate. The first one is, what does that mean, rate? When you have a solid, this movement, if you have a baseball, and you throw a baseball from one place, and baseball move from one place to B place, what does we call this? Movement, right? Movement. So if we think of this as a particle, we use velocity or we use speed to represent this, which is length divided by time. This is the speed, movement, velocity or speed. However, if you have a gas, you have liquid, how are you going to represent the speed of this movement? Liquid and gas, you cannot regard liquid and gas as a kind of a solid object, right? So there's no way to let you make a definition like length divided by time. No, there's no way for you to do this. So once you want to do this, you use this liquid or gas. We all call it fluids, not a particle, a fluid. And once we want to represent this movement, we use flow rate. We use flow rate. I hope you remember we learned this flow rate in chapter 2. Okay, so there are two ways to represent the flow rate. One is called mass flow rate. One is volumetric flow rate. So as you can understand, mass flow rate is what? Mass divided by time. This is what we call mass flow rate. Volumetric flow rate means what? Volume divided by time. So which is very different from the movement of the solid in terms of liquid and gas. And liquid and gas, well, what we call is fluids. Okay? So now let's realize what's the definition of a flow rate. Okay? For example, this is a pipe. This is a pipe, like a pipe, something like this. Okay? And you have a tap here. And the valve control the flow rate, right? If you turn it on, and this flow rate will become larger. And if you turn it off, you can shut down this flow. Okay? So the definition of flow rate, again, I told you what we say is that the mass divided by time. Volumetric flow rate is the volume divided by time. That means you open 1 second and you realize how many grams of the water in this tank. So you know 1 second and how many grams. Or you can measure the volume instead of the mass, right? So you can use the volume divided by time. Of course, if you understand you have a volume and if you measure the volume, if you measure the volume and you want to know the mass flow rate, can you do that for me? Yes, you can, right? By density. Because mass and volume, you just use the conversion factor, which is density. Okay? So this is easy. Okay, so you have mass flow rate or you have volumetric flow rate. So how are you going to convert mass flow rate and volumetric flow rate? If you have mass flow rate, we use m over dot. This is mass per time, right? V over dot is volume per time. So how do you convert mass flow rate and volumetric flow rate? By density. For example, if you have a meter, if you have a rotameter, you measure the mass flow rate, you measure the volumetric flow rate. But I say, well, I don't want you to tell me the answer of volumetric flow rate. Please tell me the mass flow rate. Can you do that? Yes, if you have a volumetric flow rate, you know the density of water, for example. Then you just put the density. You just use conversion factor to convert the volumetric flow rate times the density. It becomes the mass flow rate. This might be the Kahoot next week. Okay? Right. And now let's talk about how to do the flow rate measurement. I hope you still remember we used to introduce you rotameter. Remember rotameter? So rotameter is a device that measures the flow rate of the liquid or gas in a closed tube. This is a floater, right? And you have a reading. You have reading, floater reading. So it belongs to a, a class of the meters called variable area meters, which measure flow rate by allowing the cross-sectional areas of the fluid travel through a very causing some measurable effect. Okay, so this is why the flow stay in the middle, because the drag forces against the equal to the forces of gravity. I hope you still remember what's the definition of a Reynolds number. Inertial force against what? Dragging force, right? Remember that? Okay, anyway, so this will be stay here is because the force on the to push it up and the force to pull it down equal. So it stay here. Okay, so ladies and gentlemen, this will be definitely in your midterm exam. First, you need to tell me the definition of the rotameter. And then second, you need to draw this picture for me in your midterm exam. Well, I hate to say exam. I want to say the midterm of the celebration of learning. Okay, celebration of learning. Okay, so rotameter, please give me two information. The first one is this page. Second one is this page. Draw this picture for me. Let me understand. You understand. Okay, what is this? For information. The first one is a taper vertical tube. A taper vertical tube. Well, you can write in Chinese if you want, but I would prefer you write in English. But of course, your score won't go up. Won't goes up. Okay. Second information, flow in, fluid out. It can be gas. It can be liquid. If you have a gas in, of course, this floater will goes up, right? This flow will go up. This is the float. And you will stay here. Why? The, the, the force on the push it out to the top and the force drag to pull it down will be equal, right? It's equal. So it stay here. So the water come out or the liquid come out. And you know the reading. This is reading. And then, of course, I want you to tell me if this flow higher, that means what? Flow rate higher. If the flow rate higher, the flow will be higher. And important thing is this measure the mass flow rate or volumetric flow rate? I hope you remember. On Monday, I showed you a video, right? We count the volumes doing the calibration, right? So value of 50 millimeter. So we are measuring the volume. So this is measuring the volumetric flow rate. I want you to tell me this full information in your midterm exam. No, in the midterm of the celebration of learning. Okay? Okay, tell me what's the unit of that rotameter. Anybody want to tell me? 0.5 point. What's the unit of the rotameter we just watched? Raise your hand. 0.5, 1, 2. No, 2 is too much, right? No, you can reply me in Chinese, no problem. If you got the right answer. Anybody want to tell me? Standard what? SCFH, standard cubic feet per hour, right? So this is the unit, right? Or how about standard cubic feet per minute? That's also fine, right? Okay. So this that rotameter especially measure for what? For air. And this one showing you in this slide, especially measure the especially measure for water, right? So what is the unit of this rotameter here? Gallon per hour. Gallon per hour. Which gallon, of course, you know this is the unit of the volume. So this is the volumetric flow rate. Okay. So ladies and gentlemen, in your midterm exam, please tell me this information, and I want you to get the answer right. Okay. So do we have another method to measure the flow rate? Yes, we do. This is called orifice meter. Orifice meter is that you have this is a pipe, and the fluid flow from the left to the right, and you have a small orifice here. That's why we call orifice meter. So once the fluid passed by, the pressure dropped. The pressure dropped. That's why you see the pressure differences between enter and input and output, inlet and outlet. Okay, and you will be able to realize the volume between the pressure and the volume relationship. That's why you can get the flow rate. But I don't want to tell you too much information, because if you know how to do the measurement of the flow rate using rotameter, that'll be enough. Okay, so the information of this is the volumetric flow rate. We use rotameter. And how do you convert the volumetric flow rate to the mass flow rate? By density. Okay, and if you know the definition of volumetric flow rate, mass flow rate, what's the measurement? What's the tool you need to use to get to have the flow rate? Rotameter. Okay, rotameter. I want you to remember this word, rotameter. Okay, so that's the section chapter. Okay, do we have time? Right. So next section is chemical composition. The first one you already know how to measure the flow rate. The second one you need to know how to measure the chemical, how to do the definition of chemical composition. Okay, so if we have a mixture of A, B, C, D, E, and how do you express the composition? That's easy. Okay, so first of all, let's do the mole and the molecular weight. So what's the atomic weight? Atomic weight means what? This is a definition. I don't want to waste your time. So you know the atomic weight. So how about molecular weight? Of course, you have atomic weight. You put the atoms together, become molecular. You know the molecular weight. No problem. So please, I'll skip this quick. How about mole? Mole is that a mole of a specimen, a mole of a species in amount of that species whose mass in numerical equal to its molecular weight. Wow, this is too heavy. So you know 1 mole is what? 6.02 times 10 to 23 atoms or molecules. That's enough. Okay. So this is that what we need to know. What we need to tell you is carbon monoxide. The molecular weight of carbon monoxide. You understand? It's easy, right? Okay. So, and you can do different expressions using SI system or American engineering system. So please please do this by yourself. Just skip this. Okay, so Here is 100 gram of carbon dioxide is equal to how many moles of the carbon dioxide. So what's the conversion factor here? Conversion factor is molecular weight, right? Molecular weight. So you can do different conversion using dimensional equation and conversional factor. Okay, so we skip this quick, do this. Right, so here is important information you need to know. If I ask you, how do you find out mass flow rate from volumetric flow rate? I'm sure you are easy to tell me using conversion factor of density, right? So you can get volumetric flow rate using rotameter. So you got the data and you convert mass flow rate. That's okay. And if I ask you, can you tell me molar flow rate? So we now understand mass flow rate is mass divided by time. And volumetric flow rate is value per time. Now how about molar flow rate? Of course, you understand it's mole per time, right? So from here to here, you use what? Conversion factor of density, right? How about from mass to mole? What's the conversion factor of this? Molecular weight, right? Okay, so this might be your Kahoot next week. If I give you volumetric flow rate and I ask you molar flow rate, then you just do two types of conversion. One is using conversion factor of density and molecular weight. You got the answer, right? Easy. So I just don't want to waste your time. So these are some examples. Please practice this by yourself. I'm sure you will understand easily what I'm trying to say to you. So the section 3.3a, mole and molar weight, molecular weight. It's conversion of mass flow rate, volumetric flow rate, and molar flow rate. Right. Okay. I think okay. I think that's it for today. That's it for today, and I hope you enjoy the lecture today. You learned something from me today, and I'll see you next week.